So not all resonance structures are actually equal. Some resonance structures are better than others. The better ones actually contribute more to the resonance hybrid. Again, remember these structures don't exist, it's the hybrid that exists. And the hybrid is going to look more like the better structure. So we would have what are called major contributors and minor contributors. So far, all the ones that I've done have been equivalent. They're equal. So they would contribute equally to the hybrid. But we're going to do some that aren't equal anymore, and then we're going to learn to choose which are the better ones. So not all resonance structures equally contribute to the hybrid. Right? We could say that we have major, the major are going to be the better ones, and minor contributors. Right? We could say that some resonance structures are better. I'm going to put better in quotes because it's not that really that they're better, it's just that they contribute more to the hybrid. We're going to call them better though. Basically, the hybrid is a weighted average, right? You could say it that way. The ones that are better are going to contribute more, right? They don't all contribute equally. Sometimes they do, right? If the structures are equivalent, if one is not better than the other, then they're going to contribute equally, which is all the ones that we've looked up, that we've seen so far. So what makes one better than the other? We're going to have 3 rules, and actually let's write this. You need to take these in order. If you take these out of order, then you're likely to pick the wrong structure. So rule 1 is the most important, then rule 2, then rule 3. So use these in order. 1 is the first one you want to look at. 2 is the second one you want to look at. 3 is the third one you want to look at. So use an order when determining which structure, which resonance structure is the major contributor. Right? Is better. So again, in order. If you take them out of order, you will get it wrong. So in order. So first one. Structures with filled octets are going to be more important than those with unfilled octets. Of course, hydrogen being our exception, it never wants an octet. So when I say more important, there are major contributors, there are better ones. So if you go through and you draw your resonance structures, and you can have more than just 2, sometimes you draw 3 or 4. All the examples I've done have been kind of entry-level ones. They do get more difficult than that. Look at them and say, okay, are they all octet? If one is and one isn't, then the better one, the major contributor, is the one that's octet. If they're all octet, then we have to, or they're all not octet, then we have to go and look at rule 2. But always look at this one first. First thing you want to look at, are they octet? Remember, we're using these guys in order. So structures with filled octets are more important than those with unfilled octets. And we can use this one as an example. Put a lone pair on here, which gives it a formal positive charge. So this one, does it have resonance? It does. I can actually take these pi electrons and I can put them onto that oxygen. Remember, one of our sources, if you were to scroll back up, one of our one of our receptors, right, is an electronegative atom. So oxygen's electronegative, I can put electrons on it. So when I draw this structure, I still have, I have a single bond. I still have that sigma bond, but then I took those pi electrons and I put them on oxygen. So oxygen now has 2 lone pairs and that bond to hydrogen. Carbon still has 2 hydrogen, which gives carbon that formal positive charge when you do your calculation. So remember, the net charge has to be equal. Both of these have a +1 net charge. And then if I was to ask which one is, more important, which one's better, which one is the major contributor to the hybrid, we're actually to pick this first one because everything is octet, that wants to be octets. If you look at carbon, it has 2, 4, 6, 8 electrons. Oxygen also has 8 electrons. If I look at the second one I drew, carbon here only has 6. So this one is all octet. This carbon, not octet. So this first one is my more important one. That's the one that's going to contribute more to the hybrid. My second rule, better structures, or the more important structures, however we want to say it, have a minimum charge separation. So better structures have a minimum, probably better to say separation of charge. So by that I mean, if you have something that has a net charge of 0, it could have no formal charge, or it could have a +1 and a -1, that would still give it a net charge of 0. Or it could have 2 positives and 2 negatives, that's still a net charge of 0. So separation of charge, it's better to have the one that just has no charge. That's better than the one that has a +1 and a -1. And then that one's better than the one that has 2 positive charges and 2 negative charges. So separation, you want less formal charge. Remember, net charge is always going to be the same. So an example for this one. And if I do my formal charge calculation on this oxygen has a positive charge, and then this oxygen has a -1 charge. And then for resonance structures, and again, this is one, you might end up drawing, because I have lone pairs everywhere, right? Well, not everywhere, but I have lots of lone pairs. And I have that double bond, right? Those pi electrons. So again, when you're learning, it's very, very likely that you're going to move the wrong ones. I know how to do it, so I'm just going to draw the correct one. But as you're going through these on your own, just make sure when you look at your answer that you're not breaking octet rules. Because if you do it wrong, you're going to get something that doesn't work. So just make sure you're giving everything a critical eye. So I'm going to move those lone pairs down to that carbon. That means that carbon would end up with too many electrons unless I move something else. So I'm going to take those pi electrons and I'm going to move those onto oxygen. Resonance arrow. So oxygen now has 2 lone pairs, just the sigma bond because we moved those pi electrons. Single bond to carbon, right? And now I have a double bond to this oxygen because I took one of those lone pairs and I moved them down and made a pi bond with them. If I do formal charge on this one, I actually don't have any formal charge. So this is going to be my better one. They both have a net charge of 0. It's just that this one has no charge separation. I'm saying less, but you could say no. Less charge separation. Remember, the net charge has to be the same, but that's our better one. One more rule, there's only 3 of them. And this last one says that if the charge separation is the same, then it's better to have a negative on the more electronegative atom and then the positive on the less electronegative atom, or electropositive. You can actually use that term if you want. So if the charge separation is the same, it's better to have the negative, if you have one, so the negative charge on the more electronegative atom, and the positive, if you have one, on the less electronegative atom. So the negative on the more electronegative, the positive on the more electropositive or less electronegative atom. So an example for this one, we'll do a triple bond this time. We haven't seen one of those in a while. Triple bond means I have 4 pi electrons, right? There's 2 pi bonds there. Formal charge calculation gives me a negative on oxygen and a positive on nitrogen. So resonance, again, I'm just going to draw it, but these are really good practice for you. Kind of like take the structure just as I have it now, put it on scrap paper without looking at the answer, and then see that you can get what I'm about to do. I would even just pause the video and try it on your own, and then see if you get what I got. If you didn't, take a good look at what you have, because you're probably going to see that you broke the octet rule someplace. So I'm going to take this lone pair. I'm actually going to put a double bond, so I'm going to move them down here, and then I'm going to displace 2 of those electrons, 2 of those pi electrons onto carbon. When I draw that, so I have a lone pair on this carbon. I now have the sigma bond and 1 pi bond, right? Because I moved the 2 of the 4 pi electrons onto carbon. That's that lone pair. Nitrogen now has the sigma and the pi, and then oxygen just has 2 lone pairs because I moved 2 of those to make that pi bond. When I do my formal charge calculation now, I still have a positive on nitrogen, but I have a negative on carbon now. Also good practice for you to get your formal charge. So go through, count them out if you have to. So of these 2, which one do we like better? Right, they both have the same charge separation. They both have 1 positive and 1 negative. The positive is on the same atom in both of them, right? It's on nitrogen, so it's the negative that's different. On the one on the left, it's on oxygen. The structure on the right is on carbon. Oxygen's more electronegative, so this is the one we'd like better. So our reason, negative charge, is on the more electronegative atom. Be careful if I go back up. Remember I said to take these rules in order? So I'm going to go up to my first example. This one right here. If you were to do this one based on the 3rd rule, you're actually going to pick this one as your better structure because the positive is on the less electronegative atom. Here, the positive is on the more electronegative atom, and rule 3 tells us that we like this one, I keep highlighting, that we would like this one better. But remember, we have to use these in order, and octet trumps charge. So the fact that that first one is all octet and the second one isn't, we still like that first one better. So just be careful, right? We have to take these rules in order. So octets first. If they're both octets, then look at charge separation. If the charge separation is the same, then look to see what type of atom that charge is on. So let's just go through a couple more examples, and then I will turn you guys loose to practice this on your own. So kind of what we're going to do is I'm going to give you a structure, and then we're going to determine whether or not it has resonance. If it doesn't, we're going to say why. If it does, we're going to draw the resonance structure showing all movement with curved arrows. We're going to choose the major contributor and then say why it's the major contributor. So this one, does it have resonance? Our first question. So does it have a source, that lone pair, or that pi bond? Yes. Does it have a receptor? Adjacent to it, I have an atom with a formal positive charge, so I do. With all of these, it would be really good practice, just like I had suggested before. Once I draw the structure, before you watch me go through the answer, to pause the video and try it on your own. So pause it, give it a shot, and then hit play again after you've practiced or tried it so you can see the answer. Because just watching me do these isn't the same as doing it on your own, right? When I'm doing it, it probably doesn't look that bad. When you're just faced with this structure on your own, it's a different story. So please take advantage of the fact that this is recorded, and you can hit pause and rewind anytime you want. So definitely pause, practice these, watch my answer, and then do the same thing with the next couple. So I have a source, I have a receptor. I can move these over here. Resonance arrow, make sure you draw the resonance arrow. So I now have the pi electrons over here and the positive charge on this side. It's also good practice, this guy's horribly messy, it's also good practice with skeletal structures. I'm going to do these with skeletal structures. When you guys are practicing them on your own before you look at my answer, it might be, you might need to add hydrogens and that sort of thing. To be able to tell. It's hard to tell if something's breaking the octet rule if you're not visualizing those hydrogen. Like I've done skeletal structures enough, I can visualize them even though they're not shown. Until you get pretty good at it, that can be difficult. So this is my answer. Is one better than the other? And they're actually not, right? Both of these have a non-octet atom. The carbon in both cases that has the formal positive charge isn't octet. It has one hydrogen on it. So they both have the same separation of charge, and they both have the positive on carbon. So these are equivalent. They would contribute equally to the hybrid. That says the. How about this one? So again, please pause, try it out on your own, and then come back and we'll compare notes. So this one does have resonance, and I have pi electrons. I have an electronegative oxygen, so I'm going to move those electrons onto that oxygen. Again, make sure your arrows are pointing to where you're moving those electrons to. So I now just have that sigma bond because we moved the pi electrons. I have two lone pairs. And then don't forget formal charge. I have a net positive charge on my first one, which means I have to have a net positive charge on this one, and it happens to be on this carbon when you go through and do your formal charge calculation. So of these two, are they equivalent, or do we like one better? And if we do like one better, which one is it and why? And this is the one we like better. How many of you guys fell for my trap? This one was a trap. The second one isn't octet, the first one is, but this is the one where I do have the formal positive charge on an electronegative atom. So people that aren't taking those rules in order will normally pick the second one because of the charge. Remember, the rules have to be in order. Octet trumps charge. So this is my better one because it's all octet. How about put an oxygen in our ring here. And we'll put a double bond and a lone pair, and then another double bond. So again, please try it on your own. So this one, I'm going to move those electrons, and then, and actually let's do it in 2 steps. You could go right to one, but we haven't done one like this. So I'm going to do this one twice. I'm going to move these electrons onto that oxygen, very similar to the one that we just did. So I have 2 lone pairs there. And then there was just 1 hydrogen here, right? So there's still only 1 hydrogen here. So that carbon has my formal positive charge. I'm going to get that out of my way though. There's actually another structure for this one. I have pi electrons here. I have an atom that has a formal charge that's non-octet. So I can move those over. I now have the double bond there, and my positive charge is on this carbon. So of these 3, which one do we like better? And it is possible that 2 of them are the same and both of them are better than the others, so you would circle 2 of them. That's actually not the case here. This one's all octet. I tried to trick you again. These 2 are not all octet. If you have a carbon with a positive charge, it's not octet. Okay. Let's do one more. So nitrogen, double bond to an oxygen, single bond to an oxygen. So I got 3 lone pairs here and a negative charge, 2 lone pairs. I don't always draw lone pairs, but I will always put the charge on it, and then based on the charge, you know how many lone pairs it has, right? So that oxygen, the last one I drew that I didn't put the lone pairs on, because it doesn't have a charge, I know that it has 2 bonds, which it already has, and 2 lone pairs. So this one, there's actually a lot of structures we can draw. So when you give it a shot, you're gonna have more than one answer. So option 1, I'm going to take those to put in. That would give nitrogen too many electrons, so then I'm going to move those out onto oxygen. You can't move these, right? If we move those, we'd be breaking a sigma bond. So your only option, I just erased it, your only option is to move those pi electrons. So nitrogen, it now has a single bond to oxygen, and then that oxygen has 3 lone pairs. I have a double bond over here with 2 lone pairs, right? Because one of those non-bonding pairs became those pi electrons, and then between the nitrogen and the oxygen on top, the pi electrons moved and became the lone pair. And then this side, I didn't do anything with. Nitrogen still has a positive charge, and then oxygen has a negative charge. I do have another option. I can move one of the lone pairs on the oxygen on the left, or sorry, right, in to make a pi bond. That would give nitrogen too many electrons again, so I'm going to move these out onto oxygen. So negative charge there. This is a single bond again because we moved those pi electrons out onto oxygen, making a lone pair. I now have a double bond on this side. I only moved one of the lone pairs, so it still has 1, and then the bond to hydrogen. And then this oxygen still has, nitrogen has a positive charge, but so does oxygen. So of these, which do we like better? Yeah, you guys are picking these. So if we look at them, all three of them, remember the net charge has to be the same on all resonance structures. So the net charge is actually 0 on all of them. The two that I circled have one positive and one negative, so those sum to 0. The one down here that I'm currently circling, but we'll get rid of, has 2 positives and 2 negatives, so it's also has a net charge of 0. But we like less charge separation. These guys have the same charge separation, so they're going to be equivalent. So those two are equivalent and then better than the third one. All of them are octet. We would have checked that first. So all of three are all octets, and then I go to charge separation. So do some practice problems. If you have questions, please make sure you let me know. And then when we meet for our live session, we can go over some of those questions.